This is an introduction to the Michelson interferometer lab for the intermediate lab, spring of 2017. The student learning outcomes for this lab are several. One, to understand the interference of light. To observe interference fringes, which are just really cool. And we see interference fringes in our world a lot and don't realize that's what's going on. To also appreciate the sensitivity of the interferometer. And we'll think, it says in the lab write-up, and you'll think a bit about how this sensitivity is a great measurement device. It's been used to attempt to measure the ether, which was discovered to not exist, and also it's been used to measure gravitational waves with LIGO, and gravitational waves have been discovered to exist. So the Michelson interferometer is a very sensitive device, and you will see some of that sensitivity in today's lab. We'll also use this lab to measure the expansion function of a piezoelectric crystal. These are really common in a lot of devices that change size based on voltage or vice versa, create a voltage based on the change of size. The specific lab objectives are, one, to build a Michelson interferometer. There are some suggestions in the lab handout. Two, to observe interference fringes using a camera at the output of the interferometer. And as you observe the interference fringes, explain the difference in the fringe patterns between when you put a lens before the beam splitter and after the beam splitter. In other words, when you have circular spherical wavefronts in your interferometer, and when you have planar wavefronts in your interferometer. Make sure that you save your camera images as you do the lab. And three, you'll find the displacement of the piezo stack, which is under one of the mirrors, as a function of voltage. And in order to find the displacement, be sure that you actually take a data table and plot your data using one of the plotting packages that you like. So we're going to do a little description of interference, some of the qualitative and quantitative descriptions, and then talk about the Michelson interferometer. So these are a few pictures of things we think of when we say waves, and waves interfering with each other. We've got waves all around us. Sound and light are the most common. Water waves are also very common in our experience. And when they meet, they do interesting things. They overlap. They constructively and destructively interfere. These are all things that you are probably a bit familiar with, and so we'll review those concepts here. One way to look at interference is through a FET simulation. So we're going to just jump to the FET. This FET shows light coming from a single source. And this is red light. We can change the wavelength. We could make it purple light, lavender light. Maybe we can't. Oh, there we go. So we can make the light bluer, redder. Notice that the difference between the blue light and the red light is that now the blue light has shorter wavelengths, higher frequency, shorter wavelengths. This is light coming from one source. We would call it one source. And there is no interference. We're simply seeing peaks and troughs as the waves travel. And our screen here doesn't have any variation. If we turn this into two lights and we watch the interference of two lights, we'll see an interference build up on our screen here. And what we're seeing is that there are certain places where these waves add up to make a bright area, and certain places where their waves actually cancel each other out. And we call this constructive interference and destructive interference. We'll go through these details. You can find the FET at the FET website. Feel free to check it out. So when we talk about interference from two sources, we'd like to be able to describe when the interference is constructive and when it's destructive. If we look at these, let's say this picture on the top here has two sources which are separated by some distance, and the white wave is coming from one source and the pink wave is from another source. What we want to look for is at some distant point, so we'll say this dot here is our distant point, do the crests and peaks match up or not? So if they match up, then the interference is constructive. If they don't match, it's destructive. When we look at this point here in the gray image, these two have, the two sources are creating a crest and a trough in the same place. And so we actually have a destructive interference, or at least not completely constructive interference. This plot from the FET shows it a little bit more clearly. Here in the center, we have a crest traveling out from this source, crest, crest, and crest arriving here. A crest also travels from this source and arrives here, and they match up. That would be constructive interference. While here, and along this line, you can see that there's a mismatch between crests and troughs, and so we get destructive interference. We commonly plot these with these waves showing two waves either matched up or mismatched. So the bottom two curves here on the constructive side are both completely matched up, and they add together to make a bigger wave. That's called constructive interference. On the right here, the two waves are out of phase and they add together to make zero light. So these are mismatched. In other words, there's a crest where the other wave has a trough, or there's zero for both. And these waves always add to zero, which gives us totally destructive interference. You'll notice I said they're completely out of phase, or they're really 180 degrees out of phase. So is another picture emphasizing the same thing. Constructive interference here shows that when the waves are added, the new amplitude is larger than it was originally. And destructive interference shows that when the two waves are added, the new amplitude is smaller than it was. So what wave interference actually is, we're going to get into the mathematical explanation of it now, is the addition of electric fields. We have two waves from sources S1 and S2. They're traveling distances L1 and L2 to get to a point P. The electric field from each wave would be written like this. E1 is a magnitude and direction, E0, 1, times a phase term. This term oscillates with time and with position. That's why it's called our phase term. Tells us whether we should be looking at a crest or a trough or somewhere in between at every instant in time and space. So we can simplify that by simply saying E0, 1, e to the I, delta 1. Our second wave, E2, is the same thing except with different subscripts. So we can see that for a distance L1, R1 would be L1, and R2 here would be L2, for example. And our frequencies might be different. Could be lots of things going on here. The phase is the most important thing as we look at the addition of these waves. And it is the oscillating term delta, delta 1 and delta 2, showing, we said, where in its oscillation, crest to trough to crest again, the field, the electric field actually is. So that means here the phase example would be 0. This would be a different phase, etc. And once we have a full wave, our phase is now 2 pi. So 0, pi, 2 pi, etc. as we travel along. A full cycle of a wave is 2 pi phase. And what we look at, remember, is not an electric field, but we look at irradiance, otherwise called intensity. And to find the irradiance that we would actually see at some point P, we actually look at the electric field magnitude squared. So if those are our electric fields, the irradiance is going to be given by this expression, where the essential part here is that we are squaring the electric field. Notice that it's the electric field times its complex conjugate. That's where this delta term comes from, and the dot product as well. So the magnitude is of E is E dot E star, where each of those are vectors. So if you write out all of your terms, you end up with this expression. I would love to go over the details if you'd like to go through the math separately. So this interference term is part of this expression. The intensity I, or radiance I, is I1 plus I2 plus this boxed term. This is the interference. It changes with delta. Right? And the variable delta, this delta is the phase difference between the two fields. Delta is delta 2 minus delta 1. We care about this delta. So the phase difference delta comes from a difference in optical path length. The optical path length could be a difference in distance or a difference in material. So you could have an optical path length difference by sending one wave through glass and the other through air, even though they travel the same distance. Or you could have them travel different distances, or both. Anything that changes the optical path length of the two sources. So, interesting note, what does this say? What does this expression say about polarization and interference? This is our interference term, E1 vector dot E2 vector. That term is 0 if E1 is perpendicular to E2. In other words, if there is no polarization, no electric fields in the same direction, the interference term will be 0. So that means that we must have the same polarization in our two arms in order for interference to occur. That's why we use a laser that's polarized. It gives us the best interference, the best magnitude of the interference. So let's come to the general description of constructive and destructive conditions in terms of phase. So looking down here, notice that this picture with the two red lines that add up, the phase here is either 0, in other words, they are not shifted relative to each other, or 2 pi. So any shift of 0 or a full wavelength will end up with the same wave, and those will add to constructive interference. So you'll see here that constructive interference would say that the phase difference is 2 pi times m. And for destructive interference, we want to shift by pi, not 2 pi, but odd multiples of pi. And in order to write odd multiples of pi, we have 2m plus 1 times pi. If the phase is only due to the path length, then we can look just at the path difference, delta L. So let's say delta L is L2 minus L1. Look at the path difference, and delta L is equal to the phase difference times lambda over 2 pi. If you check out the units here, notice that lambda is units of length, and delta L should also be units of length. The delta and 2 pi are both unitless, or units of radians. And this lambda over 2 pi is saying what fraction of a wavelength is delta. So we find the phase difference and multiply it by lambda over 2 pi to get the actual path length difference. This will be important as you're thinking about different length arms or length paths in your interferometer. So in general, our two sources would give this expression that we saw before, I equals I1 plus I2 plus 2 times an interference term, cosine delta. But if our direction, as in polarization, and wavelength, and initial power, initial irradiance of each wave is the same, then we get something a bit simpler. So in our interferometer, we'll have an interference expression like this. We can simplify that a bit more and get this additional term. We will be spending our attention on the phase difference term, and when we see constructive and destructive interference, those would be the most important features, the most important mathematical details that we're going to get into. When we overlap two beams, we see an interference pattern, and this is just a sketch. It shows two beams that are overlapping like this in the plane of the board, and we see an interference pattern. So that's the kind of interference pattern you'll see, although yours will be slightly different depending on your overlap. All right, so let's get into our interferometer. Our experimental setup in schematic, you can sketch this for your pre-lab, is going to look something like this. You've got an input beam, a beam splitter, and two mirrors. Light is reflected off the beam splitter to one mirror and transmitted through the beam splitter to another mirror. This mirror will move. It's on a translation stage. And then the combined light, in other words, this beam comes back, goes to the camera. This beam comes back to the beam splitter, also reflects off and goes to the camera. The combined light is imaged on a camera. So this gives you a little description of that, what's happening at the beam splitter and how it's recombined. And then if you think about it mathematically, notice that your difference in path length is equal to 2L2 minus 2L1, or the other way around, doesn't matter which. And your job in the pre-lab is to relate this to the phase, delta, and your intensity would be 4I naught cosine squared delta over 2 for some particular phase. All right, so before you get to the video portion of this video, in other words, the live video portion of this video, here's a top-down view of what you'll see in the lab, what you'll set up actually. You're going to have the components. You've got your laser, and your laser will be more or less set through to this point down the table. So reflecting off one mirror, another mirror, give yourself a bit of room, and then to a beam splitter. Your job is then to place your two mirrors and overlap them such that you get interference. The video describes that in a bit more detail. This is what your setup will look like for the Michelson interferometer experiment. The laser beam is, as usual, just a laser beam that's polarized in some direction. You can choose what polarization direction you want. To have good interference, we simply want the beam to be polarized. The beam is going to enter the interferometer setup around here. And the primary components of the interferometer are a beam splitter, which is this cube, and two mirrors. So a beam splitter, mirror, and mirror. The light comes into the beam splitter and is split into two paths. So one path goes this way, one path goes this way towards the two mirrors. These are approximately the same distance, but for this experiment, it's not essential that they're identical. One mirror, though, is on a translation stage, and that means that it can move closer and further from the beam splitter, which means that the path length of this arm can change. So our beams come into the beam splitter, are reflected. Your job will be first to have very nice overlap, very nice reflection of the two arms back on themselves. And then here we see the two spots together. If I severely misalign the two arms, we'll see two separate spots. And then I can bring that, there are many knobs with which you can turn to align and misalign, and you'll have to decide which you want to use. When the beam splitter is aligned, you'll see either lines, which are kind of hard to see, fringes, or you'll see this kind of vibrating bright and dark as I hold on to the arm. So what I'm seeing is a maximum and a minimum, bright and dark, that you may or may not be able to see with this camera. Okay, so behind this is a camera, and you will use a camera to image your interference pattern. The couple more things about the setup. So we mentioned that this mirror will be translating back and forth. And what's interesting is that holding onto a knob and turning it just changes by so much. We know that simply changing the path length by a fraction of a wavelength will make our interference pattern change. So we want to be able to control the path length by very, very, very small increments. And for that we use a piezo. So this is a piezo crystal. It's a little ceramic, or it's a piezoelectric crystal that looks like a ceramic. And this piezo has two leads. There's one of these already in place in this translation stage. And you can see two leads back here with alligator clips going to a power supply. So this is putting out about 100 volts right now. And as I change the voltage, the piezo crystal expands and contracts. So that's what we're going to use to actually change the path length of the interferometer. In order to see the fringes very clearly, we can do a couple of things. One, we can put diverging or converging lens after very close to the beam splitter, and that will just make our beam expand. And so we can see that it's larger here. In fact, if you can see this on the camera, it looks as though there's a big line crossing in front of the beam path. And if I press on the mirror, I change the path length, and that pattern changes. So this is a good way to simply expand your beam. Or you can create spherical wave fronts by creating a spherical wave, putting your lens in front of your beam, of your interferometer. And now what I see is a bullseye pattern. See a dark or light spot in the center surrounded by several concentric rings. And what I'm seeing is the overlap of two spherical waves created by a lens here placed in the beam. So all of this will be imaged onto the camera, and you will change the path length using the piezo control. The video describes the rest of the setup and looks at this layout in detail. So before you come to lab, write the questions and your answers in your notebook. First, make a quick sketch of the basic layout, and you can do that based on the image in the previous slide. Then derive an equation for the phase between the two waves, and by waves I mean two arms, two beams, as they arrive at your detector or camera or screen in terms of the path lengths L1 and L2. 3, if the two beams overlap horizontally, what do you expect to see? Vertical or horizontal interference fringes. By horizontal, that means that two beams are coming towards each other at with a slight angle in the plane of the table. In other words, in the horizontal plane. And will your fringes be vertical or horizontal? And lastly, how much, by the way, for that one you can just sketch it. Give a quick description and sketch it. Lastly, by how much should the movable mirror be translated in order to see the interferometer output change from a maximum through a minimum and back to a maximum? So this should be an actual distance in terms of the wavelength. How much should the movable mirror be translated? This will help you as you calibrate the piezo crystal, so this is a very important piece to be comfortable with as you come into lab. Getting started is the usual, and look at the lab handout for a bit more detail. See you in lab.